Okay, my name is Carrico with the San Diego Air and Space Museum, and we're at the museum, and today is September the 28th, 2017, and today we're talking to William Burke Hare, spelled H-A-R-E, retired Lieutenant Colonel, United States Air Force, and he's going to tell us about two things: the GPS satellite system and spacecraft, and also something about Space Camp, which is pretty interesting as well. So I guess I should just call you Will. Is that the good one, or should I call you Burke?
Burke.
Burke. Okay, Burke. So, and by the way, if somebody watching this, if they look up his name on the internet, you'll find some very interesting things.
It's not my fault. I had nothing to do with it.
There's some mass murders back in 1830, I think it was, in England. So
that's right.
Anyway, so what is your current job is?
Well, I'm retired from the Air Force, and I'm a government support contractor now.
And so can you tell us the name of the company you work for?
I work for a little company called Canvas Incorporated out of Huntsville, Alabama.
And what do you do? What do they do?
It's an engineering services company.
Okay, and so, but you are currently involved with the GPS satellite systems?
Not any longer, no.
Okay, well, the other thing you're involved with, I think, had to do with three initials, and it had to do with detecting nuclear explosions, as I recall.
Well, if you mean flying GPS, I mean, yes, I flew GPS, and there's the U.S. Nuclear Detonation Detection System that actually is resident as a secondary payload on the Global Positioning System satellites.
Well, we have in our museum, let's talk about the GPS first. In our museum, we have a GPS spacecraft.
That's right. You have the world's only true GPS spacecraft on display in the world.
Why don't you hold up one of those pictures there?
There you go.
Okay, right, and we're going to talk about it a little bit as well as we can here. Maybe you can hold it up. And
sure.
When were these things in service?
So GPS 2 and 2A, so there was a GPS, they were in blocks. So GPS Block 1 was in service early on. Those were our test birds. And they lived till about 1995, 1996. So I recall GPS 2 started launching around 1989, I think, was the first launch of a GPS 2. And then they concluded with the final launch of the final GPS 2A, which was this spacecraft with a couple of modifications to it. In 1998, and I had the opportunity, or 1997, excuse me, I had the opportunity to actually be part of that launch and operationalizing the last version of this spacecraft as part of my job back then.
So this was one of 32 that were made, I believe, of that particular series?
Yeah, this is SVN-12, and satellite vehicle number SVN-12. And SVN-12 is a very interesting bird because while it has the number 12, the 11 before it were actually the GPS Block 1 satellites. So as I understand it, this is the first of the Block 2 series.
Why do we have it?
I don't know why you have it, but it's brilliant. Rockwell International built it. I don't know how you got it, but I can tell you a little bit about this specific satellite.
Please do.
This satellite was a test and checkout satellite. So Rockwell was concerned that they wanted to make sure that everything that they put on the satellite worked before they threw it into space. So this vehicle, just like the Space Shuttle Enterprise was the test space shuttle for the Space Shuttle series, SVN-12 is basically the same thing. It was designed to do all the testing. So it did environmental testing, it did all the thermal testing, it did all the vacuum testing, it did all the electrical testing. All the subcomponents were tested and checked out here on Earth to make sure that this spacecraft would operate when launched into space. What's unique about it is no block of GPS since has followed that engineering path. In other words, when the GPS-2R spacecraft was built and put together by Lockheed Martin, it was launched, and there is no test vehicle. They just used their first vehicle as the test vehicle, and then they launched it. So this is the only GPS satellite that's on Earth right now in its complete form. And rumor has it, all the components of this spacecraft are still resident inside this spacecraft. And that's a big deal, because this actually can be a reference spacecraft for how did they build GPS satellites.
Maybe we shouldn't tell anybody.
I don't know if the atomic clocks or anything are in there, but I know that there's supposed to be a lot of the subcomponents, and from what I looked at it, I noticed a lot of the actual components are still on this vehicle.
Well, why don't you point a few out with your finger there? We
Okay.
might walk out to the floor later.
Sure,
on.
sure.
Can you hold up a little more this way and get the big reflection?
Yeah. Hey, like that? Is that
Yeah,
better? Okay.
sure.
So these are your primary solar arrays here that provide the power to the batteries to the vehicle. These are your passive louver systems for thermal control. They actually close when the vehicle needs to be warm. They actually passively close, and then when the vehicle gets to a certain temperature, they actually will open and actually vent heat out of the spacecraft. And there's several of these in different
How does
quadrants.
it vent heat in a vacuum?
It actually operates as kind of a heat sink, and
It's not air blown over.
no, it's not air blown at all.
right.
It's very passive. There's
Okay.
nothing that happens other than it just opens up, and it just gives that thermal path to escape the vehicle. This is your S-band antenna. This is your telemetry, tracking, and commanding antenna. So to talk to the spacecraft, we talk to the spacecraft, and the spacecraft talks to us on this antenna right here. These right here, and here, these are your sun sensors. These sensors actually point at the sun, and they allow these solar arrays to automatically track the sun. So as the spacecraft is moving, it has an orbital period of 12 hours. As it's orbiting the Earth, we want to keep the solar arrays pointed at the sun for the most amount of time possible.
Orbital period of 12 hours, what does that mean?
That's one orbit. The spacecraft will orbit completely around the Earth in 12 hours.
Oh, okay.
And it's at somewhere between 11,000 and 12,550 miles above the Earth. 17,000 miles an hour is its orbital velocity. So it's in a mid-Earth orbit.
Okay, so that's right. You're going the same velocity, but you're going a lot further because you're further out in space. Okay.
Correct.
All right, I got it.
Correct. This spacecraft also is really neat because it has up here. These are your thrusters here, and then while not in this picture, but in the other, you have your thrusters in the bottom. So each one of these is a little thruster valve for our monopropellant, which was hydrazine. And of course, when you run out of propellant, you're done. So we didn't like to use these unless we absolutely had to. We had other internal mechanisms, reaction wheels, for instance, that we would use to maintain positioning with the spacecraft.
Inertial navigation sort of stuff?
Gyros. It was a type of gyro, yes.
Right.
But as they got saturated, we would, at some point, they couldn't absorb any more momentum. And so we'd actually have to spin them down, and we'd actually do that with an opposite thruster fire to the opposite direction that the reaction wheel was actually spinning. This is a crosslink antenna right here, this yellow device here that allowed one spacecraft to talk to another spacecraft. It was a very specialized, it was for the secondary payload, the USNDS payload. These are your antenna elements that you use to talk, that actually when you get your GPS receiver out and you're receiving signals from the spacecraft, this is the part you care about. These are your L-band antennas right here.
So, how much money has the U.S. government invested in this?
At the time when I was there, it was a $9 billion investment. And of course, overall, and that investment has continued to grow over the years. These satellites were $65 million. Sorry, this is Block 2. These satellites were in the $40 million at the time when these were built.
What launched them into orbit?
Well, that's a really good question. So what launched them into orbit was the Lt.Col launch vehicle, which was a McDonnell Douglas vehicle, which is now a United Launch Alliance vehicle. There was one being launched just 2 weeks ago out of Vandenberg. There's only one Lt.2 left to be launched in the inventory. So we're getting done with Delta.
So we got to go to the Russians then?
No, we launch off Atlas V and Delta IV for GPS, and we also will probably be launching off Falcon 9 with SpaceX. with our new version.
Was Falcon 9 the one that blew up?
There was a Falcon 9 that blew off, but Falcon 9 is the one that keeps landing, and keeps returning
Okay,
back
great.
to the launch pad and landing. It's Elon Musk,
Right.
Tesla.
Right.
This spacecraft, though, what's really neat about this spacecraft is when they designed this and built this, the intent was to launch these off the space shuttle. So these were intended to launch 2 at a time out the payload bay of the space shuttle.
So was the space shuttle going to position in the place where it was supposed to go to first, and then?
Yeah, so the space shuttle would be in its nominal orbit, somewhere between 150 and 200 miles above the Earth. The back of this vehicle actually has an apogee kick motor on the back of it, and then there would be a pan.
So hold on, apogee kick motor.
Yes, sir.
What's that?
So so what would happen is, I guess the best way to describe this is to just describe the sequence. So there's a solid propellant motor on the back of this satellite that's permanently there. And you can see where it was installed. It's clearly not there because it was a solid propellant, but you can see the housing for it on the back of this spacecraft. The solid propellant was there. Attached behind that was another rocket motor that was attached to it that was called a payload assist module, or a PAM module. That entire structure was designed to sit inside the payload bay of the space shuttle. So the space shuttle would have this spacecraft all folded up, sitting on top of this PAM-D, if you will, little rocket, and they'd spin it in 2-axis, stabilize it inside the space shuttle, and then they'd have a table that kind of give it a nudge, and it would nudge out of the space shuttle, and when it was cleared at a certain time, that rocket motor that was attached to the satellite would fire to insert it into its desired orbit. And then the apogee kick motor, which is attached here, would do the final job to get it into its orbit. GPS never flew on shuttle, which is interesting because GPS was getting ready to fly on shuttle, but then they had the Challenger accident.
Yeah.
And so they decided to not fly these on shuttle any longer, and that's where the Delta-2 came along. And so the Delta-2, actually, the GPS satellites became the primary customer for the Delta-2.
Now, how many of them at any one time are in orbit?
So right now, for a nominal constellation, they have They have 24 satellites in 6 different orbits. However, they've gone to a new schema of something called expanded 24, which gives nominally 27 is their minimum number they like to have. And I read on GPS.gov, www.gps.gov, open source, that they currently have 31 operational satellites.
And these are, now this one is not, the last one of these things went dark in 2016. Correct?
That's correct. I believe it was SVN-23, one of my favorite satellites. I used to fly that satellite. It was very sad when it went.
You used to fly, what do you mean?
Well, when you send your command and control up, your commands up to the vehicle, we consider that flying. We don't consider it flying like you did in the service.
Yeah.
But we certainly, being Air Force people, we like to think that we're flying those satellites as we operate them, as they're orbiting in space. So they're flying in space, right? So we're sending our commands up.
So how long was that your satellite?
So all of them were my satellites because we would reach out and touch all satellites in the constellation had to be touched at least twice a day.
When you say constellation, you mean that's the whole package of all the satellites out there?
That's correct. That's correct. In order to have a GPS capability, you need 3 things. You need to have a command and control system, which we call the master control station. That's where the operations crew sat.
Where is that?
That's at Schriever Air Force Base in Colorado Springs, Colorado. Used to be known as Falcon Air Force Base. And then you have to have the satellites. That's the space segment. And so the space segment is all those satellites all together. And then you have to have a user segment or somebody that's using it, right? You need somebody that's going to use the segments. What I like to tell people is, and I actually use this analogy quite a lot, if you think about satellites and GPS is a capability, right? To use positioning, navigation, and timing, which is what the mission is here. You get positioning, navigation, and timing solutions from GPS. And to get that, that's one capability, but you need a lot of the satellites to do that. So I always tell people that think about like an airplane. If we think about an F-4 or an F-15, You have, when you go into combat, you have a complete package. You have a complete ability to bring a capability to bear. You have a weapon system. You yourself in that airplane are a weapon system. GPS, an individual satellite, is not a weapon system. It takes all those satellites together to be the weapon system, and it's considered a weapon system. And it's also a civil. It's also a civil thing. A civil.
Well, of all those satellites, are all of them civilian, or some of them military, or is there?
They are all bought by the Department of Defense, and they are operated by the United States Air Force. Every single one of the global positioning systems.
But then why
satellites.
is Google and MapQuest to be able to use these things?
What happened was that there was a set of signals on these satellites, and good enterprising capitalists figured out how to exploit some of the satellite signals. We have a satellite signal called L1 course acquisition, L1CA, and the intent there was to allow military users to get up on that satellite and then access that signal, and then access something called L2, which is a military reserved signal. People figured out L1 was pretty good. It was pretty good to do positioning, navigation, and timing, navigation signals, and the like. In 1999, President Clinton ordered us to turn something off of L1 CA called selective availability. Selective availability was kind of a contact lens, if you will. We were kind of dithering or messing with the signal. So that's been turned off, and so now this L1 signal is the signal that we all enjoy as civilians, and it's the gold standard for positioning, navigation, and timing around the world.
Do any other countries have this in space?
The European Union has launched a constellation called Galileo. The Russians have a system called GLONASS. The Chinese have a system that they're populating called Compass. And the Indians have a regional system. I don't remember the name of that one. And then the Japanese have a regional positioning, navigation, and timing system called Quasi-Zenit.
Why not just tap in like Google and MapQuest do and use ours?
The more satellites that you have in your receiver, the more accurate your navigation solution.
Right.
So everybody wants theirs.
So now,
as a matter of fact, there's actually a signal being provided on this spacecraft that actually, not on this spacecraft, but in the constellation, there's actually a signal that is actually compatible with Galileo's signal with the European Union. So if you buy a receiver that has that capability, you could actually use the European satellites and the U.S. satellites at the same time.
So when I was in Europe a few years ago, I used the GPS to find
Correct.
the middle of Heidelberg, but was that I was using the American satellites?
That's correct. See, we, the United States, decided that we would offer GPS free to the world.
Okay.
And that's why it's out there free to the world.
Now, when these satellites expire, do you deorbit them and put it back down into the atmosphere?
They can't deorbit. No, we have to supersync it. Believe it or not, it takes more energy to bring it from medium Earth orbit into Earth to burn them up than it takes to send them further away. So what happens is when we decommission a satellite at these higher orbits, we actually take them and we boost them to a higher orbit, a parking orbit, and then we turn them off.
How far out are they?
They're in between MEO and GEO, so in between medium Earth orbit and geosynchronous orbit.
So geosynchronous being 22,000 or so.
Yeah, it's a very crowded orbit up there. MEO is not as crowded.
Yeah, I think I read someplace that the geosynchronous is pretty well filled up right now.
It is.
Isn't that weird? I would think. I mean, when the space shuttle and the Apollo and things come back in again, all they did was slow them down about 200 knots. They didn't slow them down that much, and it starts to, gradually come down. It lands about halfway around the Earth. But you wouldn't think it would take that much to get the thing deorbited.
Well, but what they were doing, if you think about it, their orbit was an orbit around the moon and back to the Earth. So they had calculated their orbit, their perigee, which is close, was around Earth, and their apogee away was around the moon.
Right.
So their orbit was Earth to moon, as opposed to around the Earth. So it's different.
Well, no, the shuttle. The shuttle was the same way. They turned it around, fired the rockets.
Yep.
Motors. About 200 knots is all they slowed them down.
That's right. But the shuttle is sitting at 150 to 200 miles above the Earth. I mean, there's still atmospheric drag up there. It's a lot easier from an energy management standpoint to bring spacecraft into the Earth's atmosphere at that point than where these spacecraft are resident.
Yeah. Huh. I'm surprised they didn't do that. It's all very interesting. It's been interesting to learn about this, about the whole idea of everything is orbits. It's all speeds and orbits. And when you think, I mean, when I was talking, who was I talking to? I've interviewed like 3 or 4 astronauts, and it was Rusty Schweickart. He said, it's all about orbits, and speed equals orbits.
That's right.
And when they talked about, the astronauts coming back in Apollo 13, they had to hit between 4 degrees and 7 degrees angle of attack in the atmosphere, and more than 4 degrees, they were going to skip off. At 7 degrees, they'd burn up.
Right.
But if they hit it 4 degrees and bounced off of that, well, you're still in orbit.
Right.
It might take 2 years to get back, but you're still in orbit.
Right.
You'd probably run out of water and oxygen and everything else, but you're still in orbit. And then the Earth is actually in orbit, doing 60,000 miles an hour on the sun, and the sun is in orbit doing 45,000 miles an hour around the solar system.
They teach us all about parallabas. So learn your parallabas. Right. I mean, because even Voyager, right, that left and went into interstellar space, it's on just a giant parabola. Anyway, you can get rid of that. But anyway.
No, that's interesting. Thing down at the right-hand side at the bottom, or my right-hand side, that guy.
Oh, okay. Well, this is a sun shield for a sensor for the U.S. nuclear detonation detection system. That's about all I can tell you about it.
Wait, stop. So they had a nuclear detection system back then too. So I mean, when these things were these were in orbit from 1997 to 2016 or so.
Yeah.
So part of this was probably designed more of a military device than anything else.
This is actually for treaty compliance. The 1967 above ground nuclear test ban treaty. This is to valid because of the orbit. You actually can see the entire planet, and so they have a sensor there that helps. They have several sensors that help them determine whether or not we have anybody cheating in doing above ground nuclear tests.
And what's the other little smaller one?
This one here.
Right there.
Yeah, right there. This is the Earth sensor. Now this is probably the most important sensor on the whole thing. So we have sun sensors here that track the sun, so the solar rays know where to point to get the maximum amount of solar energy collected. This sensor's entire job is to point at Earth and to stare at Earth. If that sensor fails, the spacecraft can do something what you call, if you're Earth, it's pointing at you. If that sensor fails, it can lose Earth, and all of a sudden, guess what?
Yeah.
Now I've got a problem. So this is where your precise pointing for the spacecraft is. I'm making sure that I'm sitting here. I can see the whole Earth, and I'm making sure I'm staying centered on the Earth, so that I'm pointing towards the Earth, providing my signals. In fact, a very interesting thing is, and what I was really excited about in SVN12 here is, so we talked about the S-band antenna being for telemetry tracking and commanding. This is where we talk to the satellite. This is where we do everything. I mean, this is everything to tell the satellite what to do and not to do. There's one on the back, and it's on the back of this satellite. I was really excited about to see that it was still there. So if the Earth, if this white was the back of the satellite and turns to you, well, guess what? There's an S-band antenna right there, and you can talk to it and try to rescue the satellite. Now we've had what that's called a loss of Earth scenario, and it does happen. And I'm a veteran of a couple of those, so it can with this particular satellite. So things like that could happen.
Any other objects on there we didn't discuss?
No, I think that pretty much covers the spacecraft. I mean, you've got obviously you have motors inside of here that are actually causing the spacecraft to rotate the solar arrays. But I think that pretty much just covers it. I mean, it's just the gold mylar over it for thermal control. That's about it.
And they cost, you said, what did you say?
I think they were 40, if I remember right, it was 43, I said 40 early, but I think it was 43 million for these. I think the Block 2R satellite was 65 million. I think these were each, yeah.
And they're civilian use. That's what's kind of cool. So
that's right.
People wonder what the government ever does for us. Well, They give us GPS.
That's right. GPS is what we like to say is GPS has become, it started out to be a complete 100% military program, and now it's a global utility. And it's the gold standard. I mean, we're giving it to the world for free. You were asking about other systems. Galileo charges for the use of their positioning, navigation, and time
That was
signal.
European?
The European system, yeah. So their model is to charge for it, whereas we in the United States say the
Are
world,
they all?
you can have it.
Is everybody else is in the same medium orbit then?
Yes, they have their own orbits. They're in the medium
Did
Earth
I read
orbit.
somewhere where the Chinese had a way to capture satellites? They had actually looked and
Yeah,
saw one?
I can't speak to that.
Oh, okay. Okay, I'm not trying. Should we just go out there right now and talk about it to keep
Sure.
it coherent? Yeah, let's just go out and talk about it. Look up
Sure.
at the thing, because that little picture doesn't give us a very good reference about how big it is.
No. Satellite vehicle operator first, and that's the guy on the crew that's responsible for the spacecraft side, not the payload, not the GPS signal part, not all the guts that deal with the GPS part, but the thrusters and the momentum wheels and the solar arrays and all the earth sensors and all that kind of stuff. The flying side of it, if you will, the piloting side of it, if you will, versus the guy in backside, which would be what the payload person would do. And so this is a GPS Block 2 satellite. We had GPS Block 2 satellites when I was flying these things, operating these things from late 1996 to the year 2000. We were getting rid of them at about that time. There's a variant of this called the Block 2A, and the last Block 2A was decommissioned just last year in 2016. The lifespan of this satellite was 7.5 years, and we had one that lasted 25 years.
Really?
You got your tax, yes. You got your tax money. You got your, and most of them lasted that long. To be honest with you, they lasted a very long time. America has gotten their tax dollars out of these satellites. This is the only actual GPS satellite in the world that's on public display. The only one in the world. And so this is like, for me, this is like seeing my jet for the first time in my life, right? Because they're at 11, 12,000 miles above the earth. I didn't never see them. And when they're on the pad, I went to a launch and it was already encapsulated in the rocket. I never saw it, right? The only place you see them is in the factory.
So tell us what some of these items are. What are those big cone things sticking out?
The big cone things are actually the GPS antennas that actually are providing your GPS signals, your L1, your L2, and also there's an L3 in the middle. But that's where your GPS signals are coming from those cones. And that's the mission, that's the business end of GPS. The solar arrays on either side, if you see the gold covered on the far end, the gold covered devices, the boxes there, those are actually covered up, but that's where your sun sensors are. Those are actually the sensors that actually point at the sun and make sure that the solar arrays are continuing to follow the sun so you get maximum solar array energy production out of those solar arrays. And there are motors inside the spacecraft that are actually incrementing those arrays as it goes around the Earth. The spacecraft orbits the Earth once every 12 hours. So it's in eclipse for 12 hours on batteries, and then it's in solar array for 12 hours. There are not only 24 to 27 satellites in orbit right now. They have 31 that they're currently providing signals to Earth on, 31 of these, in 6 different orbital planes. Not this one, but one newer
How
one.
many? 27?
So a nominal constellation now is 27. We call it expanded 24, but they are actually using 31 to provide signals to the Earth. So 27, so all the 4 more. But anyway, so let's see, at the top up there, you see that box at the top and at the bottom, and that's actually the top, to be honest with you. They hung it upside down. But there is no up or down in space, so it doesn't matter, right? But the box on the top and the bottom are your thruster, is your thruster quads. But just like you have the thrusters just like you have the thrusters here on the service module, those are our thrusters on the top and bottom of the spacecraft right there. We used a monopropellant of hydrazine, and it's these little puffs. And the spacecraft, Earth is not a perfect sphere, and so as you're orbiting, you process off your orbit, and you want to be precisely in the right spot for your orbit. So we would have to do something called a delta V, a change in velocity, where we would actually command those thrusters to fire. That was one of my jobs. You command the thrusters to fire to bring the spacecraft back to where you want it to be. So they don't just sit there. We actually have to operate them just like the space shuttle would have to be operated. And then on the side there, those silvery devices on the side there are actually passive louvers, and they're a passive thermal system. And I believe they're open. Yeah, they're showing open. Yeah, I think they're open right now, but they would, in a situation where we were in a thermal situation where you needed to be warmer inside the spacecraft, they actually will close, and it's just completely by how much heat is on them. When they cool, they actually close by themselves. When they open by themselves based upon the temperature that they're experiencing, the temperature that's transferred to them, the energy that's transferred to them will open or close them. There's one panel off to the side there that doesn't have a louver, and the reason is, and I can't remember which component it is off the top of my head, but there's a component that sits inside that spacecraft over there that needs to be warm all the time, so it doesn't have louvers. That's why that one panel doesn't have it. The other thing that's really cool about this spacecraft is, you see the circle in the middle, top middle there? That's your Earth sensor. That's the sensor that's job is to look at the Earth. It's to point at the Earth and stay pointed on the Earth, because when a spacecraft's not pointed at the Earth and I'm looking over here, I'm not providing you GPS signal. That's called loss of Earth. Loss of Earth is bad, and we've got to go up and we've got to do some anomaly troubleshooting, and we've got to do some contingency supports. That's what we would call, when we talk to the satellite, it was called a support. So we would go up and we do an anomaly support. We do some commanding to bring that spacecraft back to point to Earth. So that's your Earth sensor up there. This pole that's pointing out with the point, the yellowish point on the end, the white pole with the yellowish point with all the gold on it, that is your S-band downlink uplink antenna. That's how I talk to the spacecraft. I have a satellite dish, or satellite dishes around the world, and I'm in Colorado Springs, and I talk to the spacecraft over those satellite dishes. They're tracking the satellite and using that antenna to tell that spacecraft what to do. I always kid my astronaut friends, they're on the spacecraft and they're flipping the switches and doing whatever, and you got mission control asking the astronaut to flip the switches. Well, we're mission control. We just tell the spacecraft to do it, and it does what we tell it. So it's the same, and it doesn't talk back. Well, it does talk back sometimes. Yeah, sometimes they do. But yeah, for the most part, they don't talk back or question when you say why you're doing what you're doing.
Do they ever communicate with the geostationary satellite?
They do not. They do not. And I didn't have a mission where I would do that. I never really had to do that because these are, like I say, medium Earth orbit. Now, I'm going to tell you something that's really cool, and you have to look for it. You have to go way out there by Apollo 9 and look back. But there is an S-band antenna on the back of this spacecraft, because and that is really cool, because we were always told there's an antenna back there, and of course we'd never seen it, and of course we've never had a situation when I was on crew where we had to worry about it. But if we were to lose Earth really badly, and it's in a spin like this, guess what? I can talk to it when its back is to me, because it's got an S-band antenna back there. So and it's an omnidirectional antenna, so I've got opportunity to continue to try to talk to the satellite while I'm trying to figure out what's wrong with it, right? And to fix it. So that's pretty cool. On the back of it also is the casing for the apogee kick motor. So when they built this particular version of GPS, they were originally designed to be launched out of the back of the space shuttle, 2 at a time. In fact, I didn't mention this earlier, but we actually had a command sequence, and there's actually commanding in the bird for us to put it into a certain mode for shuttle. And that shuttle mode was still resident in the logic of all the satellites, even though none of them wound up being launched on the shuttle. And that's because of Challenger. They launched on Delta II rockets, but they were originally designed to be launched two at a time out of the space shuttle. And so you have a PAM-D rocket, a PAM-D rocket. So it would come off the first stage, second stage of the Delta-II, and it would be in orbit. And then it has this little kick motor. It looks like a ball with a little with a little cone on the back of it that's attached to the back of that spacecraft. It would fire to get it out of Earth's orbit and send it on its way to its mid-Earth orbit. The apogee kick motor would get it to its final destination. It was a solid propellant motor, and it's actually physically part of the structure of this particular satellite. You see it in the back. It's round, sticking out of the back. So the spacecraft's all flat, and you'll see the big round thing in the back that's part of it. But the big cone right over there is a sun shield, and it's a sun shield for a sensor that's part of the U.S. Nuclear Detonation Detection System payload. So there was a secondary mission, and all this is, of course, open source. There's a secondary mission on GPS to detect nuclear detonations to ensure compliance with the 1967 Nuclear Test Ban Treaty. So that shield is a sun shield for that particular sensor that went there. So that's pretty much that's pretty much it. But what's really cool is to us, there's a lot of us out there. The GPS is a big thing, right? I mean, think of it. GPS is a global utility. It's ubiquitous. Everybody uses it, right? Everybody uses GPS, and you guys have the one and only satellite on display in the world. This is a big deal. This is like having the Wright Flyer, in your views, the actual Wright Flyer museum for space, because of how GPS has revolutionized the world. I mean, your ATMs all use GPS time. Your gas, every time you buy gas, the time signal from GPS satellites is what's used to timestamp your thing and get the information back on your credit cards. All that is using GPS. So, I mean, you guys have just a national treasure sitting here in this corner over here.
Very interesting. It's good to tell people that.
I mean, it's a big deal. I mean, and nobody knew it was here. That's the thing. I found it on accident. Francis didn't tell me. I found it on accident. I was doing my geek out.
So do you live here?
No, I came in from Huntsville, Alabama this morning. I've been up since 2 o'clock this morning, your time. But yes, sir, that's where I am now. Retired, but that's where I work. But I was just looking around for GPS, and this thing came up. Someone had taken a picture of it. Well, I took pictures. I was here last month. I took a picture of it, and I put it on the 2nd Space Operations Squadron alumni page on Facebook, and it lit up. Nobody knew it was here. Nobody knew it was here. Everybody's all excited because everybody's seen the rocket. Everybody's been to the command and control center because that's where we've been. A lot of us have been to the ground antennas, and seen that. But nobody, unless you get to go to the factory. I've been fortunate enough to be able to go to the factory and see the current newest version on orbit, the Block 2F. But unless you get to go to the factory, this is the only place you'll ever get to see one.
What is that? What is the ring around the
Yeah, right. So the ring around the space, the yellow ring there is a crosslink antenna. So that's the ability to transmit information. It's not GPS information, but it allows you to transmit information from one satellite to another satellite. And then that other satellite can pass that information down to Earth.
So you don't need the geostationary satellite?
No, we don't use geosynchronous. We don't use geostationary satellites for anything. They use us.
Okay.
Because you can actually, believe it or not, if you're in geosynchronous orbit, because of how we orbit, we're going to be pointing right at you. So you can actually do triangulation and geosynchronous off of us, even though we're in a lower Earth orbit.
I'm gonna look at the back real fast.
You get a really good view of those. The thrusters themselves are these bronze points. Those are the actual thrusters in the quad. So what's really cool is you have the service module quad right here next to this, so you can point and say, functionally, these are functionally exactly the same thing.
And then the big silver box there, what is that?
That is a subcomponent, and I can't remember what subcomponent goes in there. I'd have to go back and